Hey everyone, welcome back to the Rust Review. I'm Brandon Conkle, and on this show I cover recent articles from the Rust community, providing a summary and giving some of my own personal opinion. I've been a web developer for 15 years now, and I've really come to love and appreciate Rust for helping me achieve more of what this channel is named after, determinism. The safety and predictability of Rust is truly exceptional, and it's one of many reasons I think it's booming right now in popularity across a variety of different programming disciplines. Today's episode covers 7 different articles, starting with a cautionary tale against Rust in an early stage startup context. Then I'll move on to a new testing tool from Facebook, an introduction to shared memory worker threads in WebAssembly, a quick note about what's new in SeaORM v0.10, a new and interesting project from 1Password called Typeshare, async traits landing in the nightly compiler, and finally a detailed article on how Rust protects you when you're intentionally writing code that isn't async. Thanks for joining me today, and I'll go ahead and pull up the first article on my screen here, Using Rust at a Startup, a Cautionary Tale. So this is from Matt Welsh. He's the CEO and co-founder at Fixie.ai. They're a startup using AI to improve the way we build software. He was previously at OctoML, Google, and Apple. His article here is critical of Rust within a startup context, saying first that he doesn't want to get into a holy war over programming languages, launching right out of the gate with Visual Basic is the best language ever. So he's talked about how in a startup, engineers really want to launch features quickly. They want to rapidly evolve approaches, rework major parts of their code. And they've got a team that's also growing really rapidly and bringing on new people all the time. So in this article, he's not necessarily critical of the language itself, but rather he points out that the rapid pace of development for a startup means that quick prototyping and ease of onboarding new developers trumps the performance and safety that's Rust's claim to fame. So he's worked with Rust at a previous startup for more than 2 years, so he's gotten a good taste of the Rust experience here, and he felt like his team over time was paying an increasingly heavy tax for continuing to use Rust. He says, development was sometimes sluggish, launching new features took longer than I would have expected, and the team was feeling a real productivity hit from that early decision to use Rust. He goes on to call out some of the major reasons for this in his mind, and first and foremost is that Rust has a huge learning curve. He says that Rust requires you to learn some entirely new ideas, things like lifetimes, ownership, the borrow checker, and admittedly, he's right. These aren't familiar concepts to people working in other common languages, but I think that's the distinctive. I think that's something that sets Rust apart, is that those things happen. They are behind the scenes when you're working in other programming languages, but you just don't have full awareness or control over any of them. He says, despite being some of the smartest and most experienced developers I'd worked with, many people on his team, himself included, struggled to understand how to do things the right way in Rust, essentially. He also says that you don't have to pay that learning curve cost. You don't have to commit to that to effectively solve the kind of problems that Rust is trying to solve. So he cites Go as an example on this. He says, I can count, there it is. I can count on one hand the number of times we hit a problem that was caused by Go's type system or garbage collector in the years of building and running this service. Now, to me, this might be an indication of the exceptional talent that he's had the privilege of working with in his history. I have been working with Go for almost a year now, and I have definitely encountered issues that were caused by the type system, especially when it comes to NPEs, null pointer exceptions. In Go, it can be kind of surprising what can actually be a nil or not, and what defaults to initializing as a nil and what doesn't. And working with maps have tricky things around nils that have caught me. And there's a variety of different things that I've run into in Go that I wasn't expecting, even being a seasoned developer. So I think maybe some of the experience that he had at Google may have colored his perception here a bit. He also says that this is not the only way to solve it. Essentially, that you can embrace good testing, good linting, good code review, good monitoring to solve the same problems that Rust does. And with Rust, you have to learn these new concepts that he's talking about. He says you'll have a hard time hiring Rust developers, but in my experience, I think it's just as hard to find an engineering team that's excellent at good testing, good linting, good code review, and good monitoring, perhaps, as it is to find a Rust developer. He talks about how the libraries and documentation are immature, and this I agree with. This is something that I've seen. Rust has been around for a while, but there are some surprising rough edges. It was, I think, especially coming from a web development perspective, that's how I entered Rust. I've been a longtime web developer, and so I originally came to Rust for web servers and API services and things related to that. And the libraries there aren't particularly polished, especially compared to the amazing experience I was spoiled with in the Python community, and even compared to some of the great solutions that are in the Node or the TypeScript community right now. It's definitely a little bit less polished, and some of the widely used solutions seem to be ones that are not quite as heavily invested in, especially when it comes to things like corporate sponsorship, as in other language ecosystems. And so that can be a pro or a con. Corporate sponsorship or big projects with very detailed governance can be a hindrance. And so in Rust, you have that feel of kind of scrappiness of putting things together yourself and finding the tools that you need to build the custom solution that's just right for you. But that's not easy. That's definitely a challenge. He also talks about how essentially prototyping. He calls it roughing out new features, but prototyping is really hard for him in Rust, essentially because you can't fudge things. Draft coding, he says, is very difficult. The compiler can and will complain about everything that doesn't pass type and lifetime checking, just like it's designed to do. And he sees that as a downside because it's hard for him to throw things together and try ideas out quickly and see what sticks. So in my perspective, though, some of his downsides here are actually selling points for me. After spending nearly 15 years working with dynamic languages and experiencing chaotic and unpredictable errors in production, I want something that is strict, that does force me to solve those edge cases right away, because they have a tendency to be ignored and forgotten in dynamic languages as long as the happy path tests are passing, especially when you're in a high pressure, early stage startup environment where the moment you hit success actually might be the time you panic the most because you don't have the resources to actually deal with that success. So my perspective may be skewed somewhat by the fact that I've been working with medium to large companies for a while now. I've been away from that move fast and break things mentality for a while now. And honestly, I feel like I'm better off for it. I feel like we have given too much emphasis on moving fast, and we kind of ignore the breaking things, but it builds up. If you're not somebody who is particularly tech savvy, it can feel like things are breaking all over the place and you have no idea how to fix them. And maybe you're just bad at technology, or maybe technology is bad. But this kind of feeling that everything is broken is starting to permeate our culture, our users of software. There's a backlash against the tech sector right now that seems to be growing. And I think it's because we're not taking the time to do things right, to pay off technical debt, to make sure that these things that get put by the wayside temporarily actually get picked back up and done right when the time is right, when you've got the resources that you need. It often gets ignored in favor of new features and pivoting and trying to capture more of the market rather than taking your prototype solution and turning it into something that's production ready. I feel like in the startup world, I rarely saw companies pay off that technical debt that they accrued while prototyping, and their users ultimately paid the price with a buggy and unreliable experience. And that's what I feel like Rust can help you avoid, because it forces you to deal with that stuff before you get out to production. The compiler forces you to deal with all kinds of things that maybe they're fine, but maybe they could lead to a bad situation if you let them go. And that's what is great about Rust to me. So he does talk about things that he likes about Rust. He talks about some of the syntax, which things like option, result, and error is certainly not unique to Rust. That's something that shows up in many other more loose or dynamic languages, or in more functional languages like Haskell and things like that. So I wouldn't call that a distinctive of Rust. I really think that the borrow tracking, the ownership system, the memory safety, that really is the distinctive here. And so he's kind of missing the point because he has that perspective of rapid prototyping to find that product market fit quickly, I guess. So looking over the Reddit thread, I get a lot of my articles and information from Reddit. I think the discussion there is interesting. It can get heated at times and a little bit wild, but it's definitely has a lot of great perspectives and different back and forth on things. And so the Reddit thread discussing this topic was a pretty good one, I feel like. One of the things that they called out was this quote that he made. Let me find it here. Yeah, he says, in my experience, people generally have little difficulty moving between languages like C++ and Python. And that struck me and others in this Reddit thread a little bit odd. It may, again, betray the fact that Matt's experience in top tier tech companies like Google and Apple may have skewed his perspective a little bit. For example, this comment here, an experienced Python dev who doesn't know C++ is going to have an absolute train wreck of a time trying to figure out header files, type coercion bugs, lambda captures, move semantics, smart pointers, dumb pointers, templates, all kinds of things that we have no concept for in the Python world. And so I feel like that's going to introduce a lot of friction in switching back and forth between languages like C++ and Python. Maybe if you're coming from C++ to Python, but not the other way around, certainly. Another commenter pointed out that the article just says things like, things were slower in Rust, but there's not any attempt at substantive comparison. He just says it felt slower. Another commenter says that, or no, this is the same commenter a little further down, says that Rust has concepts that other languages don't, so you have to learn them, but C++ was included in other languages. And so his perspective is that any experienced C++ developer would pretty quickly recognize and appreciate Rust's implementation patterns, and he himself did as a C++ developer. I like this comment here. It says, in C++, they're best practices, not rules, and they can be ignored. This attitude is demonstrated elsewhere in this Reddit thread too, which I agree. There's the cavalier idea that in C++, you should do this, but you don't always have to. And Rust is strict. You have to. That's what makes it different. Oh, yes. Another comment here. I tried Go after Rust as well, and the constant nil checks annoyed me right back out of it. I even broke with my employer about this. And again, that's the NPE stuff I was talking about in Go. It's prevalent. The nil checks are something that you have to be absolutely studious about because Go is not doing any favors for you there. But there were some supportive perspectives in the Reddit discussion as well. Like this one says, as someone who was introduced to Rust, or who introduced Rust at a startup for a small cred team, there are a few things that resonate with me. But he ends up saying, would I recommend Rust for startups? Yes. The compiler helps me scale as a team lead. And I think this is how I was feeling too. It helps to be able to enforce best practices rather than just suggest them, and point out edge cases that we need to think about. Another post here said, I've had similar feelings about using Rust in personal projects. For stuff like one-off scripts where I don't need to handle edge cases and almost always trust my own input, I don't really realize the benefit of those checks that Rust does, but still slow down, or still suffer the slowdown, the cost of slower iterations due to that smaller, less mature ecosystem. I definitely agree with what he says here. I wish there was more documentation about design patterns which play well with the lifetime system, and strategies for more flexibly exploring different architectures. That's definitely something that I've felt the need for as well. There's a lot of low level information, but not a lot of great info about putting things together in a reliable production quality architecture. Additionally, this commenter said, I worked in C++ for 2 years and had a very hard time learning Rust. So it's not universal. Even somebody with experience in C++ can have trouble with the concepts that Rust introduces. Maybe you weren't using C++ in a way that is similar to how Rust's memory model works. And so in that case, it might throw you for a loop. In the end, I definitely acknowledge that it depends a lot on the context. If your startup can actually take the time to pay off the technical debt that's incurred during the prototyping phase and rebuild your MVP in a more safe and reliable way once it finally achieves that coveted product market fit, maybe you don't need Rust. I personally have been in the opposite situation too many times, though, where the prototype becomes the product and the technical debt continues to incur greater and greater pressure on the development team as their product becomes successful and grows. It should be a great thing, but it becomes a very stressful thing. And I think a recent case that really reinforces my point is Hive, the social network startup that was largely in a prototype mode. I feel like in at least in some ways when it hit big, there were things like endpoints that had no authentication or authorization at all and were just open to allow anyone to retrieve people's information. It literally had to shut down its service for a period of time. I believe it's still down right now as I'm recording this, to give their small team a chance to clean up all these egregious security issues that they hadn't had the time to resolve up until now, because it was more like I don't know if I want to call it a side project, but definitely not something that they were placing the same level of production polish emphasis on as they would have, I think, if they knew that they were going to grow by 1 million users because of this exodus from Twitter. So you don't always know when your startup is going to hit big. You don't always know if you're going to have the time or the capacity to clean up the messes you're making during the prototyping phase. And so if you can pay that upfront technical cost of complexity and learning and sharing best practices and pioneering patterns, then I think Rust helps you handle those kind of situations a little bit better. You've got the edge cases handled upfront, so they're not going to come back to bite you when you can least deal with it in the middle of a crazy production spike. Next up, I'm going to move to Facebook. The Meta blog, their developer blog, posted an article. When was it? Oh, it was just last week about Hermit, their new tool for controlled testing and software bug finding. From a Reddit thread here, I love Jason White's overview here, the TLDR note. This is a Rust project that forces deterministic execution of arbitrary programs and acts like a reproducible container. So therefore, it hermetically seals or isolates the program from sources of non-determinism such as time, thread interleaving, random number generation, etc. It is like a emulator or a virtual machine, essentially, with precise control over your software execution. So it provides features like the ability to, similar to an emulator, like if you've ever used a classic game emulator, a retro emulator that allows you to pause and rewind your game, to save your state anywhere and perfectly resume what you were doing whenever you want. Even sharing save files with other people that they can then resume on their computer to play the game at that point. Features that were never supported originally when that software came out. The goal with Facebook's Hermit tool here is similar, to be able to control the environment and deterministically reproduce these previously unpredictable and chaotic states that your applications could get into because of all of the randomness that's around it. In our daily development work, we seldom, hardly ever have that kind of a luxury. It's really hard to deal with flaky integration tests and things like that, where everything seems like it fits together perfectly, but there's some factor that you just can't figure out. There's something that you just can't understand. For some reason, 4 times when you run it, it's fine, and the 5th time it falls over and you can't figure out why. This Hermit tool is a way that you could potentially discover by varying inputs in this deterministic environment. You might be able to discover what was actually going wrong. Everything the processor and operating system contributes to your program's execution. So things like thread scheduling, random number generation or random data generation, virtual memory addresses, unique identifiers, all of that is a set of implicit inputs that you don't necessarily always have control over, and that impacts the determinism of your program. And so our standard test approaches really control for these explicit program inputs, like what you're actually sending, but they don't have any way of controlling these implicit inputs that come from the operating environment itself. So with Hermit, you can carefully control the environment. You can reproduce exactly what happened, messing around with your inputs to see what triggers a failure and what doesn't. So flaky tests and concurrency bugs and things like that are their primary use cases here. And they've got some great detail around how they're using Hermit to locate and figure out what's causing some of this random unpredictable stuff. What I liked, though, is they also have some other applications in mind, other ways that they could use this kind of reproducible environment. So beyond just flaky tests and problem solving, you could also use it for deterministically reproducible builds, being able to fully trust your packages because they were built in exactly the same kind of environment that they were tested in. Reproducible debugging, which they say has the same benefits as traditional replay debugging. I'm not actually sure what that is, so I'll click through. This is something that I've not used from the Windows ecosystem, I guess, but it's time travel debugging. So he also talks about replicated state machines that provide fault tolerance in distributed systems. They could be used for smart contracts, which are normally written in specialized languages that are constrained to make sure that they're deterministic. But these reproducible containers could make it possible to use Rust to write smart contracts or something like that. So there's a lot of different ways that this could be used. It sounds really fascinating. It's something that we've not really had access to as developers in an easy way yet. And so I think it's a great idea. I'm glad that Facebook is digging into this problem. Next up, I've got a post from Joe Neiman on the Twig blog called Threads and Messages with Rust and WebAssembly. Now, this is a fascinating article. He posted this last week talking about shared memory web workers in WebAssembly with Rust. So Joe is a programmer and a mathematician from Texas who's been using Rust since before it hit 1.0. And this article is an excellent introduction to the concept of threading with web workers, which essentially are a way to spawn new workers that share memory, like you would typically see in a programming language that has multi-threading, something like Python or Rust, of course. But in the WebAssembly world, in the world of browsers, they haven't had this concept before. It's something that's newly making its way into the WebAssembly world. He acknowledges that there are currently some caveats here, which I'll cover in a moment, but this article provides a really great overview for this interesting feature that's eventually going to make its way into stable releases. So the article does some introduction and then jumps into its core problem, which is dealing with large data. So he introduces his code here for spawning a worker and setting up a callback to handle messages when we get from the worker, using post message to send a message to the worker. And this becomes important in a moment, but this initial pass is using post message, and also inserts a bug here that will wipe the callback out of memory before it's done being used. So look, hey, this is not quite as safe of an environment as we're used to in fully Rust programming. But he also has a entry point here using Wasm bindgen for the worker to call back into our WebAssembly process here. And then here is the JavaScript code that kind of encapsulates this and calls that worker entry point that we just looked at. So when you're using the Web Workers API, he says all of the messages you send are JS values, which is fine for primitives. But then when you need to send more structured types, some of the specialized types that we can work with in Rust, you have to convert them into these JS values and back. There are libraries that help this, but it's definitely kind of a rough edge. It's low level working with all of this. And then, like I said, the main point of the article is dealing with large data, because in this case, it can be tricky because the post message function requires you to copy the data. So if you have a large amount of data, you don't necessarily want to keep copying it around in memory, because that takes a lot of work. What is normally really fast in Rust, when you have a large data structure, starts to slow things down. And if you have to do it over and over again, especially when you're sending messages back and forth in a WebAssembly environment, that can add up really fast. So he looked into ways how he can actually reuse that object in memory instead of copying it back and forth everywhere. So first off, he talks about the post message with transfer function that uses shared array buffers. And it provides an alternative that allows you to transfer ownership of certain JavaScript objects from one worker to another without copying it, but you can't directly use the objects that are living in the WASM memory. So that means you can't use types like vec, or you can't use Rust's native threading tools like MPSC channels or anything like that. If you're willing to jump through a few hoops, however, you can use shared memory web workers by passing a WASM memory object into the WASM bindgen's automatically generated init function. It takes a second optional parameter here, which is this memory object to use for shared memory. You need to build it with some extra features, however, in order to get this working. The link was broken. Yeah. But a little further down in the article, he highlights what those target features are. But you need to build it with some extra features. You need to use the nightly compiler and some unstable flags. And you have to be careful, because if you try to block the main thread, even for a really short amount of time, most browsers are going to throw an error. So you've got to be careful not to block. But he is able to get this shared memory system working, and he is able to take advantage of MPSC channels and specialized Rust tricks and things that make it easy to work with these specialized data types. So he talks about, okay, how much does this actually help? What kind of benefit are we actually talking about? And as you can see, with a 20 megabyte large data structure, post message is kind of slow on something like that, which understandable. You're copying 20 megabytes from one memory region to another. It's going to take a little bit of time. Post message with transfer, however, dramatically improves that, which is pretty much what you would expect. But remember, with post message with transfer, you have to convert it to a shared array buffer first. And so you can't directly use something like a vec. But it is a dramatic improvement over just the standard post message. And then he shows the standard sync MPSC channel, and that again increases it quite a bit. But he makes a good point here. He says it is the fastest by a substantial factor, but not by a very large absolute amount. So this is only really going to help you between that and post message with transfer if you really do need to send a lot of messages really fast. That small overhead that post message with transfer provides can add up if you're doing it a lot, but in a lot of cases, that's going to be your best solution. And that's ended up being what he chose for his project here. So the performance gain, he said, wasn't significant enough to be worth it in his case, but I could definitely see how it could be very significant in other situations. So your mileage may vary with it. Next up, I've got a what's new in SeaORM posts. If you follow some of my other videos or my blog posts or have taken a look at my GitHub caster API example, you'll know that I've been enjoying SeaORM for a while now. For over a year now, I've used it and really liked it, even though it has some pretty significant limitations. There are problems when you want to join multiple things or make more complex queries, and you end up having to drop back to cQuery in those kind of cases. But with SeaORM 0.10, they recently launched some new features, not specifically to help what I was just talking about there, but there are some interesting things that are landing here. So the first off, there are beginning to take advantage of generic associated types to infer the lifetime of database connections and make it easier to work on streams inside connections, because the stream's lifetime can be implicit now based on generic associated types. It also brings support for array types in Postgres, which is a great feature that often has spotty support from libraries in other ecosystems. I've used them frequently in a node context, but had trouble with them in Go using the popular SQLX library there, which is not to be confused with the Rest SQLX library. But I ended up having to just serialize my array to JSON rather than actually use a Postgres array type in a Go context because it was so hard. So it's great to see first-class support arrive for them in SeaORM. You can also now pull the database-specific error out of SeaORM's error types, and you can finally run migrations on Postgres schemas other than public, suggesting or selecting which schema to target based on a command line flag or programmatically. There are a number of other changes reflected in the blog post, so check it out if you are a SeaORM listener or user and you want to know more. Next up is something interesting. I did not even know that 1Password was a heavy user of Rust, but clearly they are at the very least stepping into it now because they've shared a really fascinating project called Typeshare. They call it the ultimate tool for synchronizing your type definitions between Rust and other languages for seamless foreign function interfaces. But I could see it working really well in situations where you have Rust on the server and TypeScript on the client and things like that. My son and I have been watching the Lord of the Rings movies lately, the first time for him. So I really enjoy his reference to the One Ring here in the README. But they say leveraging the power of the SERD library, SERDE, I'm not sure how to pronounce that correctly, but it's a tool that converts your REST types into their equivalent forms in Swift, Go, with caveats, Kotlin, and TypeScript, keeping your cross-language code base in sync. It can even handle generics and convert effortlessly between standard libraries in different languages, which is really cool. The TypeScript example they have in the README here is pretty simple and straightforward, but it looks great. It does exactly what you would expect. You've got this SERDE tag for type, and that translates to an actual type property on the derived mynum and TypeScript here. Like I said, beyond just FFI, I could see this being helpful in a variety of different ways. I know it's become really popular to embed Rust to share your language or your library between multiple different language ecosystem consumers. So things like Prisma or OSO or other projects are written in Rust, but deployed to all kinds of different languages. And so I could see this being really helpful in that kind of situation. They mention the Go caveats, and they say Go support is experimental, but they don't really talk about what those caveats are. So I would love to hear a little bit more about what the trade-offs are in Go. It's possible because generics are so new in Go, maybe they don't support it or something like that. But yeah, I didn't know that 1Password was using Rust, and it's really cool to see them sharing such a useful tool and drawing more attention to the community. Thank you, 1Password. Next up is something that I'm rather excited about, async function traits. An MVP is coming to nightly. So Tyler Mandry posted this on the behalf of the Rust Async working group, posted a couple of weeks ago and talked about the introduction of async fun, FN, async fn in trait. I like async trait better. That's so much more terse. Anyway, it's a big deal. So the async trait crate has been the solution to this problem, or the workaround for this problem, essentially, for a while now. It works around the trait fns cannot be declared async error when you try to include an async function in your trait. This crate, though, is specifically a temporary measure, and the author David Tolnay indicates that the compiler and language hope to deliver more in the future. We're reaching that place. We are getting to the point where we can do more. So there are some limitations, of course. There's always limitations, but as we've heard in other cases, Tyler says that the team thinks it's ready for users to give it a try and give them some feedback on the approach. So he provides an overview of the problem with async functions and traits in the first place. Why is it a hard problem? And it involves a dependency on generic associated types that, as we know, just recently was satisfied, but also the need to name the type constructed by an async trait, or I'm sorry, the type constructed by an async block in order to assign it as an associated type in an implementation. So they show here, if you have an async function that's returning an anonymous type, essentially, but you want to reference that type in an association, you don't have anything to reference. It's just anonymous. There's no way to give it a name. So there are some workarounds that are available in the stable compiler so that you don't have to bring in nightly. Chief among them, the runtime type erasure, which is what the async trait crate itself uses. With this nightly compiler, though, they're able to deliver what they'd hoped for with an implementation initially that they just recently landed in nightly. So the plan is to provide some new standardized traits, some things like async iterator that is built on this new functionality that landed in nightly, and they're letting people give it a try and give some feedback around how this works and what potential problems might come from the current MVP approach. They talk about some of the limitations, which include problems when spawning from a generic function when you're using a work stealing executor that requires spanned tasks to be sent, like Tokyo, for example, which means that most of us are using work stealing executors. So be careful about spawning. It's not possible because there's no way to really express bounds on an anonymous type like those that async functions return. And there's also a problem with dynamic dispatch, where you can't call an async function with a dynamic trait. But now's a good time to experimentally build your project on nightly and remove that async trait crate and see if you run into problems. Sounds like the team would love to hear about your feedback, and I'm really excited to see this feature progress towards production. All right, I'll finish up today with a post from Cliff Biffle, a Google alum who's worked on projects like Chrome. He was a founder on Loon. He's worked on Native Client and Google Glass. He posted on his blog, the cleverly titled Cliffle, last week about what he calls an underappreciated Rust feature, the ability to write safe code that is not concurrent or thread safe. This is a feature of Rust that's surprisingly missing in many other languages. He says, but wait, you might be saying, of course I can write code that isn't concurrent in Java or Python or C. But can you, though? He says, you can certainly write code that ignores concurrency and would malfunction if used from multiple threads simultaneously, but that's not the same thing as specifically writing code that isn't concurrent, code that can't be used concurrently, that the compiler guarantees can't be used concurrently. That is something wholly separate and something that Rust shines in. He starts with a classic bank account example with the problem that the deposit and withdrawal methods aren't necessarily atomic. So you can take a look at the implementation that he put here. So he says this means that if two threads are accessing the same account at the same time, you could end up with the following tragic sequence of events here. Thread A starts out by beginning to deposit 100. Thread B begins its operation to withdraw 100. Thread A reads the current balance in order to increment it. Let's say that it started out at 100, and so thread A is going to add 100 to that, reaching 200, but then hypothetically thread B would withdraw 100 and leave that back down to 100. But let's say thread A reads that current balance, thread B also reads that current balance and decrements it. So then thread A stores the balance after their deposit. So they incremented it to 200, even while thread B was decrementing it to 0, essentially. But if thread A wins the data race, then it stores the balance after the deposit of 200, not taking into account that 100 that thread B tried to withdraw. So thread B thinks it successfully withdrew 100 monies. Thread A thinks it successfully deposited 100 monies. It should leave the balance unchanged. It should end up at 100, but because of the data race, it ends up at 200. So this is the kind of situation that you encounter a lot in programming. You see these bugs pop up all the time, especially when you're trying to take something concurrent that wasn't before, something that you didn't realize was thread safe. And so this is when he calls this out. He says, this code was never intended to be used concurrently. There's nothing explicitly preventing it from being used concurrently, though, and that's the sticking point here. And many times engineers are going to reach for concurrency, parallelization, when they're under stress, while traffic is rapidly growing, in those kind of situations where their popularity is exploding in ways they didn't expect. And so in this case, you're often left with what Cliff refers to as non-consensual concurrency. So he says non-consensual concurrency is when your code has had concurrency forced on it. Never mind that the code wasn't written with threads in mind and it's not thread safe and it was never intended to be used that way. It's getting threads whether you like it or not. So this kind of situation ends up being fixed in a hurry after the fact. You've got, he says, if you've got an existing chunk of code that worked before those darn threads showed up, you're not going to sit down and redesign the whole thing. You're not going to rework your data structures and algorithms from scratch. You're not going to use the fancy lock-free high concurrency alternatives. No, if you're anything like most programmers, he says, you're most likely to just slap some locks on things and hope it all starts working again. But guess what? Locks can attack too. So just because you're using a lock doesn't mean your problem is solved. And he goes into some challenges with locks. So even though locks may seem like the perfect solution, they can come with a lot of drawbacks. With Rust, though, the compiler actually prevents you from trying to use that bank account type from multiple threads when it's not designed to work that way. And he talks about how Rust enables this with what he calls the engineering marvel of sync and also send. He says, by avoiding sync, we can write a whole family of related types that can't be shared across threads. It does not prevent them from being used in threaded programs. It just prevents the concurrency from leaking into the code that you're writing. So you can use it in a multi-threaded environment, but it's executed in a single-threaded way because the type system, the compiler, knows that it doesn't support concurrency. That's an amazing thing about sync that other languages, other ecosystems don't really do. And then send is kind of a complement to that. It's slightly different from sync. Sync indicates that data can be shared between threads, and send indicates that data can be sent between threads. And in Cliff's experience, problems with send most often occur in cases where you're implementing mutexes or your type is using some kind of thread local data, which would be meaningless if you're accessing it in a different thread, or you're doing some kind of logging or tracing that includes those thread names and you want to indicate consistent thread names across your execution. Those are areas where send becomes important beyond just sync. It's not as common to have trouble with send as it is with sync. Cliff finishes up with the conclusion that Rust provides a level of confidence that other language ecosystems lack. He says that Rust is the only language where he really feels comfortable writing non-thread safe data structures without caveats or fear. He says in cases where they apply, such data structures can be simpler and often faster than concurrent thread-safe data structures, which makes sense. You don't have to worry about thread safety when you're ensuring that something can only be executed in a single threaded context. So you don't necessarily need to make every data structure thread safe. And if you get it wrong, you're going to get a compiler error because Rust lets you know rather than letting you run into a weird runtime bug. Some dense topics this time. I've really enjoyed digging in and learning more about the kind of concepts that they're talking, the kind of challenges that they're overcoming in these articles. Rust has really just impressed me time and time again with the diverse applications, the diverse types of programmers that gravitate towards it, the many different ways that you can apply it, and the many different, often unexpected benefits that it brings. So digging into these articles each week or every other week has really been enriching to me, and I hope it's been enriching to you also. If you haven't checked out my Rust architecture example, I have a project called Rust Example Caster API in my GitHub at github/bconkle. That includes, I just recently did a lot of refactoring around it. I've got it working around Axum now. I've got WebSockets implemented. I've done moved to the excellent Next Test library that allows you to embrace more concurrency and parallelism in your test running, and even rewrote my integration tests in a way that no longer needed any cleanup and could take advantage of that concurrent execution to speed up integration testing radically, which I love. I also reworked the build system, the GitHub Actions, updated them, moved away from some deprecated things and towards some more well-maintained things. Really appreciate the Next Test project that I mentioned for giving me something great to copy off of largely in those cases. So check it out. And you can find me on Mastodon, like I said. I'm on the Fostodon instance. You can also find me in Discord at various programming channels, especially ones around Rust or TypeScript or things like that, or in the Denver devs community that I love on Discord because I'm in the Denver, Colorado area. You can also find me at Formidable Labs. We're a consultancy that has expertise across the entire web stack. And if you'd like to work with me on a project, I'd love to hear more from you. Thank you so much for watching today, and hope you have a great rest of your week.